There is certainly no shortage of videos about either the Spitfire Mk I or Bf-109E. So what does this one add to the table? Well, it's the first to make a really deep dive into their turn performance, using computer simulations which have been validated by actual World War II data. And while these certainly confirm that the Spitfire on the whole was a better turner, just as expected, this video will also give hard numbers on just how large or small was the difference, all the way from sea level and up to higher altitudes. In addition, we will see some exceptions to this rule, and that the Bf-109 could actually, under certain special conditions, outturn the Spitfire by using flaps. Finally, it will also debunk some myths connected to the Bf-109 slats, and also highlight why some anecdotal evidence needs to be taken with a grain of salt. So why put together a presentation like this in the first place? Well, first of all, because both aircraft are truly iconic and known almost to everyone. In addition, even people with no special interest in aviation can still often point them out, given how intimately coupled they are to the legendary Battle of Britain. Added to this is the fact that even aviation enthusiasts who know them intimately often have very different ideas about their relative turn performance. And last but not least, the simulation uncovered some new and unexpected results, which could be interesting to take a closer look at. But let's begin by comparing the aircraft's technical specifications. And what first catches the eye on this slide, when they are mirrored like this, is just how big the size difference was. The Bf-109 is just smaller in all aspects. It's shorter and has both a smaller span and wing area. And even the contour surfaces appear diminutive in comparison. But when it comes to engine power, they were actually quite evenly matched at higher altitudes. And it's therefore testament to the Spitfire's clean aerodynamics that it was just as fast as the Bf-109 at typical Battle of Britain raid heights, even though it was lugging around almost 40% more in wing area. But at lower altitudes, assuming both aircraft are run on standard 87 octane fuel, then the Bf-109 enjoyed a power advantage, and it was both faster and climbed better, also helped by being about 7% lighter. However, if we assume that the Spitfire is run on 100 octane fuel, then the tables are turned, and with a whopping 40% power increase at sea level, then the Spitfire becomes clearly superior in all important performance aspects, such as speed, climb, acceleration and turns, etc. Finally, and other than the large difference in wing area, it should also be pointed out that the Spitfire's wingspan is about 13% larger, thus cutting down on its induced drag. And last but not least, it should also be noted that the Bf-109's maximum lift coefficient at 1.41 is about 4% larger than the Spitfire's. But let's leave this overview of comparison for now, and instead look at their flap installations, since flaps sometimes have a huge impact on turn performance. And the reason for only showing the flaps of the Bf-109 here is that the Spitfire's split flap arrangement only had two positions, which was either fully retracted or 85 degrees down, thus making them unsuitable for use in turns. The Bf-109's flaps, on the other hand, here marked in red, were of the conventional type and could be seamlessly dropped to any angle by turning the outer of the two control wheels, here ringed in red. This control wheel was located together with another one placed closer to the pilot, and which via a chain and wire linkage adjusted the angle of the tail's horizontal stabilizer, here also marked in red. And when these two wheels were turned together in the same direction, this ingeniously more or less automatically compensated for the change in pitch trim caused by either extending or retracting the flaps. So in essence, this meant that the Bf-109 pilot could seamlessly adjust the flaps and trim with his left hand, while at the same time flying the aircraft with his right, and thus making the flaps perfectly possible to utilize in a dogfight. The slats on the Bf-109 were unpowered, but even so automatic, being controlled by changes in the leading edge suction forces due to changes in the angle of attack. Consequently, at higher speeds they remain closed, but at lower speeds or in aggressive maneuvering they would extend. And this began at a lift coefficient of about 0.8, after which they would gradually extend with increasing angle of attack until being fully deployed at a CL of about 1.3. And here it bears stressing that properly adjusted and maintained slats moved out gradually and did not remain in place and suddenly pop out with a bang, as for example the famous British test pilot Eric Brown claims. So this is just a popular myth, since this problem only occurred if the slats were poorly maintained, and was therefore more of a symptom of poor adjustment than anything else, and which was probably the case for the captured Bf 109 Eric Brown flew. The slats were on each end supported by horizontal levers, connected to vertical rises that were not quite in parallel, but angled in such a way that the slats moved in and out gradually with changes in angle of attack. And to avoid the slats jamming, these were in turn interconnected via a series of belt cranks and push rods to ensure that they moved in and out in unison. A common misconception about the Bf 109 slats is that they caused a lot of drag, and while the wing profile drag certainly may have doubled or even tripled when extended, their actual contribution to the total drag was still rather small, and being only in the order of 2.5 to 5% of the total, since it's not the wing profile drag, but rather the induced drag, which totally dominates in tight turns. Finally, it bears mentioning that the slats made it perfectly safe to take the Bf 109 to the very edge and extract every ounce of performance it had to give, since aileron control was mained well into and beyond stall, without any of the nasty flicking in and out of the turn that could occur on other aircraft, thus instilling a sense of confidence in the pilots who flew them. And this then leads us to the question of pilot skills, which of course has a major impact on how well an aircraft actually performs. And not so surprisingly, there is ample historical evidence that many Spitfire and Bf 109 pilots with low to moderate skill levels never even came close to utilizing their aircraft's true potential. In fact, both the German ace Johannes Steinhoff and some of the British test pilots tasked with aircraft evaluations made much the same observations. Namely, that inexperienced pilots tended to believe that they were doing really tight turns, even when more seasoned pilots had no trouble at all keeping them in their sights. But surprisingly, there are even examples of quite experienced pilots having the same difficulties in extracting an aircraft's true potential, simply by being unfamiliar with them. And this is well illustrated by Wing Commander Steinforth's statement on this page, in which he claims that the Bf 109 I delivered its best turn performance even though the slats had not even deployed, which of course is wrong. So in summary, while an aircraft's inherent turn capabilities on paper may be good, if the pilot still fails to extract it, all is for naught anyway. And this brings us to yet another important point when it comes to aircraft evaluations, which are the dangers connected to so-called outliers. And as the name implies, an outlier is a data point that is not representative of the mean or average. Consequently, and by definition really, if you use an outlier to make a prediction about an expected outcome, you're bound to get it wrong. And just to take an example, while a successful basketball player may be short, this actually says very little about the average length of NBA players in general, since if you do a meta-analysis and look for patterns, this will without doubt reveal that the top basketball players are on average far taller than most people. However, we do of course not have any similar lived experience when it comes to turn performance, and we therefore need to consult more than just one pilot count to get a reliable result. And if done right, such a meta-analysis will without doubt reveal that the overwhelming majority of the pilots who flew these aircraft all agree that the Spitfire handily outturned the Bf 109. But unfortunately, quotes like Leikhoff's and Klosterman's on this slide are still sometimes cherry-picked and passed off as representative, when they're in fact no better than pointing to a short basketball player, as typical of the NBA. And with this having been said about the dangers of outliers, what the analysis in this video will add on top of the common knowledge that the Spitfire outturned the Bf-109 is putting reliable numbers on just how big was the difference. But the analysis will also highlight that there are actual exceptions to the rule, and that under special conditions, then the Bf-109 will actually outturn the Spitfire. But again, and this cannot be stressed enough, these are exceptions to the rule, and for all practical purposes then the Spitfire, just like legend tells us, does turn very much better than the Bf-109. And with that having been said about the dangers of relying on isolated pilot quotes, let's now instead turn our attention to actual data, and begin by looking at different types of turns, and how we can measure and compare them. And here it's appropriate to begin with the instantaneous turn, since this is most straightforward and intuitive. And in this type of turn, the pilot simply holds back on the stick until he reaches the maximum allowable G-load, or the point at which the aircraft just is short of stalling, and just keeps it there. Consequently, in this type of turn, the pilot extracts as much turn performance as he can from the aircraft, even if this results in more drag than the engines can compensate for, and therefore a speed loss. And as the speed drops, the pilot will then be faced with two choices, because either he continues to pull as hard as he can, thus continuing to lose speed, until he is forced to either level out or stall. But before this happens, the pilot will reach a speed at which he will turn as tight as he can without losing speed, which in aerodynamics is known as the speed for best sustained turn rate. And to stay at this speed, he therefore needs to unload the aircraft somewhat when reaching this point and no longer pull as hard. In the figure, we can identify this point as the end of the blue curve at 14 seconds into the turn. And for the Bf-109E4 at 18,000 feet or about 5.5 kilometers altitude, the speed for best sustained turn rate is about 295 kilometers per hour true airspeed. And if the pilot unloads to maintain this speed, he will then follow the outer green curve, maintaining both speed and turn radius. While if he instead continues to ride the edge of stall, he will then follow the red curve, and while certainly turning somewhat tighter and pulling ahead, for this gain pay a price in speed, and at a 27-second point into the turn be doing only 284 kilometers per hour, i.e. 11 kilometers per hour slower than the speed for best turn rate. Consequently, at the end of the blue curve at 14 seconds into the turn, the pilot can then either continue to turn as tight as he can and trade a temporary gain in turn rate for a loss of speed, or follow the green curve and maintain speed for the best turn rate, and which will in the long run put him ahead of the pilot following the red curve. And what is the best course of action has no easy answer, because it all depends on the circumstances. Is the pilot expecting a prolonged turn fight and needs to gain angles on his opponent? Then he should follow the green curve. Or does he temporarily need some angles for a deflection shot? Then he should choose the red path. And while following the red path simply means riding the edge of stall in an instantaneous turn, let's now instead take a closer look at what factors governs an aircraft's sustained turn capabilities. In this figure, we can see something which in aeronautical circles is often referred to as a doghouse chart, with speed on the x-axis and turn rate on the y-axis. And in this example, the baseline aircraft's doghouse curve is marked in red. But different aircraft will of course have different doghouse charts, with some having the apex, or rooftop if you will, placed at different heights and airspeeds. For example, a World War I biplane would have the rooftop placed far up to the left, while a modern jet fighter would have it to the lower right in this schematic figure. However, what they all have in common is how the placement of this rooftop apex will be moved if certain basic aircraft parameters like wing area, CLmax, aspect ratio or engine power are changed. And basically, we can see two types of effects. If we increase either the wing area or CLmax, for example by dropping flaps, this will move the left-hand roof of the red doghouse chart up and to the left, as the dashed green line suggests. While if we instead increase either the power or the aspect ratio, this will move the right-hand roof of the red doghouse chart up to the right, as indicated by the dashed blue curve. So in summary, we would expect that an aircraft with a lower wing loading, say like the Spitfire, would have its apex placed up and to the left, while an aircraft with a low power loading like the Bf-109 would have it more to the right. And as we shall see when we get into the details of the simulation results, this is indeed the case. But before we do that, let's take a brief look at the simulation model itself and how it's been validated. And this traces its origins to an analytical model developed by Saab's Department for Conceptual Military Aircraft already in the early 1970s. And using this as a base, I developed my own simulation model in the middle 1980s, which then went on to become the backbone of my master's thesis, which was centered on analyzing the effects of external stores on fighter jet aircraft. After my graduation, the program lay dormant for many years, until I revived it in the early 2000s, adding the propeller thrust model needed to model also World War II aircraft in 2005. To date, all of 42 World War II era aircraft have been modeled and validated, using either flight test data or contemporary calculations from World War II. And having covered the origins of the program as such, this then brings us to the question of how the turn simulation model has been validated, and which will be covered in the two upcoming slides. So before continuing with the simulation results, let's take a brief look at how the simulation model was validated, since this not only underpins the credibility of the simulation model itself, but also by extension the results. And if we begin with the validation of sustained turn performance, I was lucky enough to find an actual Messerschmitt report from World War II on just this subject, and which covered a number of Messerschmitt designs, one of which was the Bf-109E. And in the figure from this report on this slide, we can see the turn time in seconds on the x-axis, while the y-axis shows the vertical speed in meters per second. And if the pilot allows altitude to be lost in the turn, then this can of course be used to tighten it up and turn faster, just as the figure shows. However, since we're interested in sustained turns, this by definition means that both speed and altitude should be maintained, and which is why we will read off the values on the thicker horizontal line, which represents zero vertical speed. And if we look at the line representing zero flap deflection, we can read off a turn time of 18.5 seconds at sea level and 33.2 seconds at 6 kilometers altitude in the Messerschmitt report. While in the C++ simulation model, using the same assumptions as the Messerschmitt engineers used in their calculations, this yields 18.5 and 33.7 seconds respectively, which has to be said to be quite satisfactory. Taking our leave of the sustained turn performance validation, let's now instead take a look at how this was done for instantaneous turns. And the big difference here is that there, to the best of my knowledge, exists no such data for either the Spitfire Mk I or Bf-109E, which we could use to validate with. However, we are even so fortunate that there is actually other instantaneous turn performance data on the Bf-109, albeit not for the E4, but data calculated by Messerschmitt themselves for the later Bf109 K4 model. And using the same assumptions as the Germans did to validate the C++ model, the agreement between the data points is remarkably close, thus indicating that the C++ simulation model as such should be quite capable of also simulating the Bf109E4 and Spitfire Mk I, provided that these aircraft's physical characteristics are entered into the simulation model. Because all aircraft are bound by the same laws of aerodynamics and physics, and as long as we take their physical differences into account, then the simulation results for both the Bf109 and Spitfire should be sufficiently close for us to be able to do a fair comparison and draw conclusions about their relative turn performance. As we saw on a previous slide, it is physically possible to drop the flaps on the Bf109, even during combat. But this still leaves the question if there is any solid evidence that this ever happened in real life. We do know that using flaps in combat was not the norm for Luftwaffe Bf109 pilots, and that it was far more common to keep the speed up and use dive and zoom tactics. However, it does seem that slow-speed turn fights with the flaps extended did even so occur sometimes, as these two quotes connected to the German ace Hans-Joachim Marseille shows. And in addition to these two anecdotes connected to the Bf109, there are also other examples connected to other aircraft types as well. For example, this one by US Army Air Force ace John Godfrey, who in the closing stages of World War II had an inconclusive dogfight with a Focke-Wulf 190 D9, in which he dropped the flaps on his P-51B Mustang to tighten up his turn. So in summary, we can conclude that trailing edge flaps were actually used in combat. And although this was probably more an exception than the rule, it did still happen, and which is why some of the following slides will show turn performance for the Bf109 both with and without flaps. If we begin by looking at the sustained turn performance at lower altitudes and start off with the turn rates, which are depicted in a left-hand chart, we can conclude that the Spitfire Mk I is untouchable if it is running on 100-octane fuel. And the reason for this is that the extra 250 horsepower 100-octane fuel provides over standard 87-octane fuel allows it to simply pull itself around by brute force, as seen in the dotted red line, which towers way over the other curves in this chart. Interestingly though, if we look at the turn radiuses shown in the figure to the right, we can see that there is basically no improvement in turn radius, other than that the Spitfire can maintain its shorter turn radius also at higher speeds. But if we drop the 100-octane discussion and instead compare the aircraft when both are running on standard 87-octane fuel, as in the solid red and blue curves in the left-hand figure, we can see that there is not much of a difference in turn rate. Granted, the Spitfire is still slightly better at lower speeds, but even at such modest speeds as 250 km per hour true airspeed and above, then the Bf109 can actually turn faster. But when it comes to turn radiuses, we can, by comparing the solid red lines in the right-hand chart, see that the Spitfire is significantly better, with a turn radius that is only about 87% of the Bf109's. However, the Bf109 does have one ace up its sleeve. If it drops flaps, it can actually turn both faster and with a shorter turn radius than the Spitfire at this altitude. And the difference is, as we can see from the dashed blue lines, quite significant, both when it comes to turn rate and turn radius. Also note that this superiority in turn radius remains even if we assume that the Spitfire is flying on 100-octane fuel, since as long as the Bf109 slows down enough, it will still be able to stay inside the Spitfire's turn. Consequently, and somewhat paradoxically, we can conclude that irrespective of the Spitfire's and Bf109's reputations from this time, There is actually an exception to the rule, in that the Bf-109 can actually outturn the Spitfire, albeit with flaps only. Consequently, we can conclude that the anecdotes about Hans-Joachim Marseille outturning enemy aircraft in a Bf-109 with flaps dropped are not just some wild stories, but are also perfectly possible from a theoretical standpoint, just as long as the pilot is skilled and determined enough to extract every last bit of performance from his aircraft. And with that having been said about the turn performance at lower altitudes, let's now shift our gaze and compare the aircraft at typical Battle of Britain raid heights. And just as expected from theory, once the air gets as thin as it does at higher altitudes, then the Spitfire's bigger wing area starts to become a big asset in turns. But if we begin by setting the stage for this comparison at the Luftwaffe's typical raid altitude of 18,000 feet during the Battle of Britain, or about 5,500 meters if you will, it's important to note that the Spitfire cannot benefit from 100-octane fuel at this altitude, since this is above the Merlin 3's full throttle height, which means that the power output from the engine is the same irrespective of which type of fuel is used. Consequently, the Spitfire is only represented by one solid red line at this altitude. And if we begin by comparing the Bf-109 with no flaps extended, we can see that the Spitfire is, as expected, significantly better both in turn rate and turn radius. However, by dropping flaps, the Bf-109 can still slash its turn radius at this altitude. And as we can see in the right-hand chart, the improvement is quite significant, as it now turns with an even shorter turn radius than the Spitfire. But when it comes to turn rate, as we can see in the left-hand figure, then the Bf-109's engine power at this altitude is not enough to compensate for the large increase in drag caused by the flaps. And the turn rate actually drops somewhat, albeit still allowing it to fly slower and turn tighter than the Spitfire. However, this advantage must be said to be rather more academic than practical in nature, since turning at such low speeds and at such high altitudes with a Bf-109 would be nothing short of suicidal if other RAF fighters were around. But in summary, we can still conclude that it was theoretically possible for a Bf-109 to turn tighter at such altitudes. And in a 1 versus 1 scenario, when both fighters gradually slow down in a turn fight, then yes, the Bf-109 could theoretically avoid being shot down by dropping flaps. But in the long run, the Spitfire could just stay at a slightly wider turn radius outside the Bf-109s, and instead of turning faster, use the excess energy thus made available to gradually climb upwards, and then swoop down and finish off the Bf-109 with an instantaneous turn from a higher altitude. And this mention of instantaneous turns then naturally leads us to the subject of the next slide, which is a comparison of both aircraft's instantaneous turn capabilities at this altitude. And on this slide, we can immediately see that the Spitfire is clearly superior in instantaneous turns at higher altitudes, which of course is just as expected, because the higher you go, the thinner the air, and the lower the air's density is, the more valuable a bigger wing will become. And in these figures we can see what would happen if both aircraft entered into a maximum rate all-out instantaneous turn at 18,000 feet and at 560 kilometers per hour, which was close to their top speeds at this typical Luftwaffe raid height. In the right-hand figure, we can see that both aircraft can initially attain 6 Gs, which is also assumed to be their maximum allowable G-load. However, the long dashed red and blue lines tells us that the airspeed drops off dramatically at the same time, due to the copious amounts of drag the aircraft experiences when turning this hard. But here the similarity ends, because while the Bf-109 reaches CL max already 1 second into the turn, The Spitfire's bigger wing means that it can maintain the maximum allowable G-load for much longer and only reaches CL max about 6 seconds into the turn. And as we shall see from the bird's eye view on the left, it's really only from about 4 seconds into the turn when we begin to see a marked difference, with the Spitfire not only pulling ahead, but also doing so with a shorter turn radius. And from here on there is not much to add really, other than observing that the Spitfire here is in its element and continues to turn inside the BF-109 with ease. And the only thing we can note as being better for the BF-109 is that its speed has not bled off as much as for the Spitfire at the end of the trace 16 seconds into the turn, where it is roughly 10 km per hour faster than the Spitfire. However, this can hardly be gauged as an advantage, but rather as a consequence that its wing simply cannot sustain a lift force as large as on the Spitfire, and that it consequently does not slow down as much due to this, and not because it performs any better in the turn. If we again shift our gaze to the figure on the right, we can begin by noting two things. First of all, the two vertical lines at 16 and 18 seconds, which show the time it takes for both aircraft to complete a 360-degree turn. The other thing to note in this figure are the endpoints of the colored lines that end at 39 and 46 seconds respectively, and are the times it takes for the Spitfire and the BF-109 to do 2 complete turns at this altitude. Interesting to note here is that both aircraft have to unload to maintain speed for best turn rate just short of completing 2 complete turns, which is at about 37 seconds for the Spitfire and about 40 seconds for the BF-109. But other than that, there is in some sense nothing remarkable about this figure, since it only confirms what we already knew from anecdotal evidence, which is that at higher altitudes, then the Spitfire could handily outturn the BF-109 due to its larger wing. However, what both these figures do bring to the table is that they give us actual numerical values, and by so doing a more solid base on which to compare the two, rather than just being able to say that one was better than the other. And if we then make the same comparison of an all-out turn at close to the top speed, as we did on the previous slide, but this time at lower altitudes, the air is now so dense that both aircraft can maintain the maximum allowable G-load for far longer, with both aircraft managing to hold 6 Gs for a complete half turn before becoming CL max limited. And what this means in practice is that while a pilot certainly can pull 7, 8 or maybe even 9 Gs momentarily, he is assumed to pull only the maximum allowable Gs until the speed has bled off to the point that he reaches CL max, at which time he is assumed to unload and ride the edge of stall. Note that at 12 and 13 seconds respectively, when the Spitfire and BF-109 have both completed a 360-degree turn, both are still at a speed higher than the speed for the best turn rate, and both still at CL max. Another important thing to highlight here is that it looks like the BF-109 has a better turn performance, since it's turning with a smaller radius. And while this is certainly true, it's actually only because the BF-109 has a higher span loading. And because of this, its induced drag is higher and consequently it slows down faster. And since both aircraft are still G-limited, this makes the BF-109 turn tighter. This can also be seen in the right-hand chart. Both aircraft turn with basically the same performance for the first 5 seconds. But after this, the BF-109 is CL max limited, while the Spitfire is still below CL max until about 8 seconds into the turn, meaning its turn rate will increase until then. And a careful observation of the lower right-hand figure also reveals something else. Paradoxically, the 100-octane Spitfire is actually hampered by its high performance output, since this does a better job of keeping the speed up, meaning it will actually turn worse until about 9 seconds into the turn. And from this follows an interesting conclusion, namely that in the initial stages of an instantaneous turn at high speed, it actually pays off to reduce throttle. And to illustrate this, we can again look at the bird's eye view on the left, where there are two curves for the BF109, and conclude that the BF109 at the reduced throttle setting of 0.6 ATA actually turns better than at the 1.3 ATA combat power setting. However, note that reducing throttle only pays off in the initial stages of the turn, because once you slow down sufficiently to reach CL max, both the BF109 and Spitfire will turn better the higher the power setting is. And with this having been said, it's now time to wrap up and take a look at what conclusions can be drawn from these simulations and make a summary of lessons learned. First of all, and something that hardly comes as a surprise, is that the simulations confirm that the Spitfire Mk I could handily outturn the BF109 under most conditions. And while this of course is already well known, and can just as well be concluded based on a meta-analysis of anecdotal evidence, we now also have numbers on just how large or small was the difference at different altitudes and speeds, and with different power settings. But we have also concluded that there are actually some unexpected and somewhat surprising exceptions to this rule, and that the BF109 could actually outturn the Spitfire by dropping flaps at lower altitudes and speeds. In addition, that this advantage was not just limited to a shorter turn radius, but that the BF109 could, by dropping flaps, actually attain a higher turn rate as well. On the other hand, it could also be argued that this was more of an academic advantage, since few would say that dropping flaps and getting into a slow-speed turn fight would be the best way to fly a BF109 to its advantages, and that it should rather be used to do high-speed dive and zoom attacks, just as common wisdom dictates. But be that as it may, history has also taught us that 1 versus 1 dogfights could and did occur, and that both Allied and Axis pilots did actually sometimes resort to using flaps, even under combat conditions. But connected to this, it's also important to note that the BF109E's ability to outturn the Spitfire Mk I by dropping flaps is only possible if both aircraft are using standard 87-octane fuel. But with the Rolls-Royce Merlin instead running on 100-octane fuel, then it becomes a no-contest win for the Spitfire. But then again, with the substantially higher power output that 100-octane fuel provides, this elevates the Spitfire to a whole new level, not only when it comes to turns, but also in terms of acceleration, speed and climb performance as well. And if you want to know more about how the Spitfire Mk I and BF109 compare not only in turns, I have written a whole book on this subject. And while this book's focus certainly is on aircraft performance, comparing the Spitfire Mk I and BF109E with different fuels and engine alternatives, it also contains an analysis of the state of the art in aircraft procurement and design at the time, looking into aerodynamics, engines, armament, and some hypothetical scenarios as well, such as what would have been the effects of a more efficient cooling system or a more powerful engine on the BF109's performance. And what would have been the result if Reginald Mitchell had been allowed to design a Spitfire with a smaller wing area, similar to that on the BF109, and would this have been a good idea or not? And for all these different aircraft versions, i.e. both those that made it into the service and the hypothetical, the book makes a detailed analysis of how their speed, climb, turn, acceleration, dive and zoom, and energy retention all would have been affected. In addition, if you also have an interest in World War I aircraft, I have written a book about this time period as well, covering the speed, climb, turn, acceleration, dive dive and zoom, and energy retention performance of these aircraft as well. And this book covers most of the famous late war fighters of the time, such as the Fokker DR-1, D-7 and D-8, and the Sopwith Camel and Triplane, SE-5A, Newport 28 and SPAD 13, just to name a few. In addition, on my homepage, you will find a number of papers I have written on the subject of aircraft performance, covering both World War I and World War II aircraft. And these are available as free downloads in PDF format, and give a good idea about the contents and the type of information contained in my books. Finally, thanks for watching, and I hope you found this interesting. And if you'd like to see the next video I'm working on, which will cover the Sopwith Camel and Fokker DR-1, then please consider liking this video and subscribing to my channel.